Hey guys, welcome back. In this video, I want to take you through another example on surface integral of vector field. So suppose we have a solid E, which is bounded by the following two surfaces. First, we have the surface given by z equals square root of 8 minus x squared minus y squared, bounding the region from above. And second, we have the surface z equals square root of x squared plus y squared, bounding the region from below. Furthermore, we are going to let S be the closed boundary of the region E with positive orientation. Right, let us visualize this region E over here in the XYZ space. Notice that the equation z equals square root of 8 minus x squared minus y squared is the upper hemisphere of radius square root 8. Imagine we have the upper hemisphere over here with radius square root 8. Now the other equation z equals square root of x squared plus y squared is actually the upper half cone, which looks something like this. So our region E must consist of points that lies above the cone and below the upper hemisphere. In other words, the region E is given by the shaded region over here. Okay? And the surface S, which is the boundary surface of our region E, comes with the positive orientation, meaning we have unit normals pointing away from the solid. Right, notice that the surface S consists of two parts. One that comes from the upper hemisphere, bounding the region from the top, and the other part of the surface S comes from the cone, which bounds the region from below. So we can partition S into two surfaces, S1 and S2, where S1 is that part of the surface at the top and S2 is that part of the surface at the bottom. Now coming back to our question, here we want to compute the flux of the vector field F given over the surface S. Well, basically this is just the surface integral of the vector field F across the surface S. Since S is the union of S1 and S2, we can write this as the sum of the surface integral across S1 and that across S2. Alright, let us begin by computing the surface integral across the surface S1. Now the surface S1 is part of the upper hemisphere, which lies above the cone. One way of parameterizing the surface is by means of the spherical coordinates. In this case, the parameter rho, which measures the distance from the origin, is always a constant. In fact, this is equal to the radius of the hemisphere, which is given by square root 8. So next we are going to determine the range for the parameter phi and theta. Now recall that the angle theta is the polar angle made by the ray coming out from the origin on the xy plane with the positive x-axis. Since in our case we are going one round about the z-axis, the range for theta is between 0 and 2 pi. So the parameter will take on the interval from 0 to 2 pi. On the other hand, the parameter phi measures the angle made by the ray coming out from the origin with the positive z-axis. Well, from the figure, it seems that we need to take all the angle for phi starting from 0, since we need to cover the point on the z-axis, all the way until we reach this cone whose equation is z equals square root of x squared plus y squared. But remember, this cone in terms of spherical coordinates is given by phi being equal to pi over 4, which means the value pi over 4 is the upper bound for the parameter phi. So the parameter phi will take on the interval from 0 to pi over 4. Alright? With this, we are now ready to write down a vector function that traces out the surface S1. Namely, we have the vector function r depending on phi and theta, where the first component is given by this expression here, since x in general is given by rho times psi phi cosine theta in terms of spherical coordinates. Since rho is square root of 8 in this case, we have this expression here in the first component. Likewise, in general, the variable y is equal to rho times psi phi times sine theta. So substituting for rho, we have the expression here in the second component. And finally, the variable z is equal to rho times cosine phi. So substituting for rho again, we have square root 8 times cosine phi in the last component. And together with the range for our parameters, the vector function r will trace out the surface S1. As with any vector function tracing out a surface in space, there are two possible orientations arising from our vector function r. Namely, we either have the normal given by r phi cross r theta, or r theta cross r phi. So these are two vectors which are normal to the surface traced out by the vector function r. From our previous study, the vector r phi cross r theta is actually upward pointing, whereas the vector r theta cross r phi is downward pointing. Now in our case, the surface S1 comes with the upward pointing normal. This is because the surface S in the question has positive orientation, and the positive orientation induces upward pointing normal to the surface S1. Hence, we are going to use the vector r phi cross r theta as our normal when calculating the surface integral. Well, without giving you the full details of the calculations, I've written down here the vector for r phi cross r theta, as well as the dot product of our vector field f and this vector. So with this, we can now evaluate the surface integral of our vector field f across the surface S1. So using the vector function r, this can be converted into a double integral over the parameter domain D of the dot product of our vector field f and r phi cross r theta. So this vector is chosen because we are interested in the upward pointing normals. But remember, the parameter domain D is given by the range or the intervals for the parameter phi and theta. So expanding this double integral, we are going to replace dA by d phi d theta, where theta is bounded between 0 and 2 pi, and phi will take on the interval from 0 to pi over 4. So after substituting for the integrand, which we obtained previously, over here, we now arrive at the following iterated integrals in terms of theta and phi. And after some simplifications, we arrive at the answer, which is 8 pi. Alright, so this is the surface integral across the surface S1. Let us now move on to the surface S2. Well, this time we have the surface which is part of the cone, given by z equals square root of x squared plus y squared, lying below the hemisphere, whose equation is z equals square root of 8 minus x squared minus y squared. Now, in order to determine the range for the variable z, we need to solve for the intersection curve. So if we combine these two equations, we'll have square root of 8 minus x squared minus y squared being equal to the square root of x squared plus y squared. Squaring both sides, we'll have 2 times x squared plus y squared equals to 8, and so x squared plus y squared is equal to 4, which means the intersection curve of the upper hemisphere and the cone is this circle here of radius 2. Okay? And if we substitute that into the cone equation, we have z equals square root of 4, which is 2. Well, this means that the intersection curve is a circle of radius 2 on the horizontal plane z equals 2. Imagine we have the horizontal plane over here, given by z equals 2. The intersection curve of the upper hemisphere and the cone is a circle of radius 2 on this plane, centered around the z-axis. Alright? Well, the question is, how do we parameterize the surface S2? Well, one way is to think of S2 as a collection of circles with different radius. Imagine we have a circle of radius u coming from the surface S2. Then notice that the height of this circle from the xy plane is also u, because z is equal to the square root of x squared plus y squared. Since the radius is u, if we substitute this into the cone equation, we have z being equal to square root of u squared, which is again u. Hence, we can think of S2 as the collection of circles with radius u, whose distance from the xy plane is also u. In other words, if we set u as our parameter for the variable z, then we can trace out the circle by using the angle v. Namely, we can set x to be u cosine v and y to be u sine v. So the vector function r will trace out the surface S2, provided v varies from 0 to 2 pi, since we are taking the full circle around the z-axis, and the variable u must be bounded between 0 and 2. Since u, representing the variable z, must be bounded between the xy plane and the plane z equals 2. Next, let us consider the orientation given by the vector function r. Well, the surface S2 must be oriented downward because the positive orientation of S induces downward orientation for the surface S2. Therefore, in this case, we are going to use the normal vector given by RV cross RU. Without showing you the calculation, the vector is given by the following components. Notice that the last entry is negative because the parameter u is generally positive. Hence, this vector RV cross RU is indeed pointing downwards. Furthermore, the dot product of our vector field F and this normal vector turns out to be the following expression in terms of u and v. Again, I didn't show the calculations here. So finally, the surface integral across S2 can now be converted into the double integral over the parameter domain, where the integrand is now the dot product of our vector field F and RV cross RU. So next we're going to replace this double integral by the corresponding iterated integrals in terms of u and v. So here, dA is replaced by du dv, where v is bounded between 0 and 2 pi, whereas u is bounded between 0 and 2. And the integrand is the function in terms of u and v for the dot product we obtained previously. Right, after some calculations, the final answer is minus 8 pi. So that is the surface integral, or the flux, across the surface S2. And finally, by adding up the surface integral across S1 and S2, we arrive at the final answer for the surface integral across S. So here, the final answer is actually 0, which means the total flux across the entire surface S is actually 0. Okay guys, that's all for now. See you next time.